This is the exercise for regularization with dataset of housing prices in MS. So let's move on to our first question. What we'll have to do over here is we'll have to import the data and encode categorical variables. So for importing the data, firstly we'll use a read underscore CSV function from pandas. So as you can see over here, this line of code reads a CSV file named housing.mas.csv using pandas library read CSV function. The contents of the CSV file are loaded into a data frame object named df. So df.shape over here is used to print the shape of the data frame, which represents the number of rows and columns in the dataset. And dot head function over here displays first few rows of the data frame. So next what we will have to do is we will have to display all the columns over here. So what we will do is we'll use dot set option for it. So this line of code sets the display option in pandas to show all columns of the data frame when using df.head method by setting pd.set option with parameters of display max function to none. All columns in the data frame will be displayed instead of truncating the output. The df.head line is used to display first few rows of the data frame again, not showing all the columns. Now showing all the columns. So now what we'll do is we'll try to get dummies. So using this line of code, what we are trying to do is we are trying to encode categorical variables in the data frame by creating dummy variables using one-hot encoding. So pd.getDummies function is applied to data frame df, and resulting data frame with dummy variables is assigned back to uh, df. So drop underscore first equals true. This ensures that uh, we are dropping the first category for each categorical variable to avoid collinearity issues. So convert what get the dummies does is it converts categorical variables into dummy indicator variables, and each variable is converted in as many variables as there are different values. So columns in the output are each named after a value. If the input is a data frame, the name of the original variable is prepended to the value. So let's check what's happening over here. So as we can see, we can view street column in this above uh, dotted function, but over here down below we will not be able to see that specific column, but what we are able to see is street underscore pave. So each variable from the column will have separate columns in the dummies as dummies. So we'll get even for lot shape we'll get each variable will get different columns over here, as you can see. So this is what dot get dummies is helpful for. So it removes first category to avoid collinearity and original variables are dropped. Moving on to our next question. So what we have to do over here is we have to report the skewness of price and log of price. So as you can see over here, the code mentions that these lines calculate and print the skewness of the price column in the data frame df. So df.price.skew function computes the skewness, which is measure of the asymmetry of the distribution of the price values. Positive skewness indicates longer tail on the right side of the distribution, while negative skewness indicates longer tail on the left side. So that's what we are able to see over here. The skewness for normal distribution is 0. So a skewness value of 1.68 indicates that distribution is skewed to the right. Moving on, .hist function is used to create a histogram to visualize the distribution of the price values, as we can see over here. So in next part of our code, what we are trying to do is we are trying to create a new column named ln price. The np.log function from NumPy is used to compute the logarithm. Taking logarithm can be useful in situations where data has a skewed distribution, as it can help normalize the distribution and make it more symmetric. So dot skew over here prints the skewness of ln price column, as we can see over here at 0.37 along with a lot of decimal points. So taking logarithm decreases skewness. Moving on to our next question, what we have to do is we have to define y and x over here, and we have to standardize the predictors. So looking at the code over here, what we are trying to do is we are trying to remove the price column from the data frame using drop function. By specifying axis equals to 1, it indicates that column is being dropped. This step is performed because the target variable price has been transformed into a logarithm transformed variable ln price and is assigned to variable y over here. So variable y is assigned the values of ln price column, and when we are talking about x, what is happening is it's creating a new data frame by dropping ln price column from original data frame using dot drop function. And axis equals to 1 represent column wise transformation over here. So let's see how we can perform standard uh, how we can standardize the x over here. So what we are trying to do is this line standardizes the predictors in the data frame x using standard scalar class from scikit-learn. The standard scalar class standardizes the features by removing the mean and scaling to unit variance. The fit transform method is called on the standard scalar object passing the data frame x as the input. It computes the mean and standard deviation of each feature in x and performs the standardization, returning standardized predictors as NumPy array. Moving on to our next question. Here what we have to do is we have to use standardized predictors. So we have to run ridge regression using shrinkage parameter 1 to 200 with step size equals to 1. And later on we have to plot the estimated coefficients as a function of the shrinkage parameter. So let's see the code here. We are using a range function in this code. So this line over here creates an array A using the arange function from the NumPy library. The arange function generates a sequence of numbers from start value 1 to stop value 200 with a step size of 10. Resulting array A will contain numbers such as 1, 11, 21 up till 191. So arange function is similar to the built-in function range in Python, but it allows for non-integer values and returns a NumPy array. Next part of code over here, what it's doing is it's creating an instance of rich class from scikit-learn library, which is a linear regression model with L2 regularization. And over here, we are trying to create an empty list called coefficient. So let's see how this loop is working over here. What's happening is the loop iterates over each value in the A array. So these lines perform ridge regression using standardized predictors x underscore std and target variable y for a range of shrinkage parameters specified by array A. In each iteration of the for loop, a ridge regression model M2 is created using a ridge class from scikit-learn, and uh, the setParams method over here is used to set alpha, which is a shrinkage parameter, to the current value I from the array A. Then the fit method is called on the M2 model, passing the standardized predictors and target variable to train the model. Later on, the estimated coefficients of the model are appended to the coefficient list in each iteration. At last, to view the shape of the coefficient, we use dot shape function. So the number of alphas and number of predictors can be viewed in this list. Let's try to understand the plot over here. So these lines create a line plot to visualize the estimated coefficients as a function of the shrinkage parameter. The plot function from the matplotlib library is used to plot the array A on x-axis and coefficient list on y-axis. So the x dot x label function and dot y label function are used to set labels for x-axis and y-axis, as we can see over here. Alpha would be x-axis and ridge coefficient would be y-axis. So by executing this code, you will run ridge regression with varying shrinkage parameters using standardized predictors and target variable. The resulting estimated coefficients will be plotted against shrinkage parameter values, providing insights into the impact of regularization on the coefficients. This plot can help identify the optimal shrinkage parameter for the ridge regression model. This is how we have successfully plotted the estimated coefficients as a function of the shrinkage parameter. Now let's see what do we have in our next question. Using standardized predictors, we have to run ridge regression along with shrinkage parameter 1 to 200 and step size equals to 10 using leave one out cross validation. And at last we have to report RMSE. So over here what we'll have to do is we'll have to use a ridge CV regression to using standardized predictors and target variable with leave one out cross validation. So this ridge CV class, as we can see over here, is from scikit-learn and is used to create a ridge regression model M2. So alpha's parameter is set to array A and store CV values is set to true, indicating cross-validated predicted values and will be stored in the M2 model. The fit method is then called on M2 model to train it. Later on over here, this line of code calculates the mean squared error for best performing alpha value found by ridge CV model. To view the shape, we are using dot shape over here. So this line prints the shape of CV values attribute of M2 model. The CV values attribute stores cross-validated predicted values obtained during leave one out cross-validation. So this shape represents dimensions of cross-validated predicted values, and first dimension being number of samples and second dimension being number of alpha values used in ridge regression. And at last, to find RMSE, we are using dot square root function over MSE2. So the calculated RMSE value is assigned to variable RMSE2. So by using this variable, we are trying to return value of RMSE. Therefore, by executing this code, you will perform ridge regression with leave one out cross validation and using standardized predictors and target variable. The resulting best models MSE and RMSE will be reported, providing an evaluation of the model's performance. The RMSE is a commonly used metric to measure the average difference between the predicted and actual values, giving an indication of how well the model fits the data.